Hi everyone, today we're going to talk about equilibrium. What I'd like you to be able to do is describe what conditions are occurring when a chemical reaction is at equilibrium. So we're actually going to talk about three types of equilibrium. We're going to focus on chemical equilibrium. We're going to start with a do now on energy diagrams and then take our notes. So if you don't already, you're going to need your notebook and you might want your notes on energy diagrams out and ready to go. Alright, so here we have a energy diagram. Again, potential energy on the y, reaction coordinate on the bottom, which just means time's passing as our reaction occurs. My first question for you is this energy diagram for an endothermic or exothermic reaction? Hopefully you picked endothermic. Our products have more energy than our reactants. Energy has been absorbed during this reaction, which means it's an endothermic reaction. Next, we're going to identify what the arrow represents. Which of the following arrows represents our activation energy of the forward reaction? Just a quick reminder, when I say forward reaction, I mean we're reading this diagram from left to right like a book. Reverse reaction would be reading it from right to left. Hopefully you picked number 2. Activation energy is the amount of energy it takes for the reaction to start, which is represented by arrow 2. What is the potential energy of the reactants? So I could have also asked this as what is H reactants or enthalpy of the reactants. That is arrow number 1. So A is representing our reactants, and this represents the energy of them. Which arrow represents the potential energy of our products? Arrow number 4 represents the energy of our products, be our products. And lastly, which one represents the heat of reaction? Just a quick reminder, instead of heat of reaction, I could have also asked delta H. I could have also asked which arrow represents the difference between the enthalpy of our products and the enthalpy of our reactants. While you don't have many choices left here, it is arrow number 3. And again, it's the difference between our product energy and our reactant energy. Reversible reactions is something that you've actually seen throughout the year and we've touched on a little bit before. In fact, just a moment ago, I basically touched on it when I said you could read the energy diagram forward and backwards. Not all reactions are going to be reversible. For example, when you're baking a cake, there's a bunch of chemical reactions occurring as you bake a cake, but you can't unbake the cake. That is not a reversible reaction. So there's a specific subset of reactions that are reversible. And again, what I mean by reversible is that the reactants can make the products, but the reverse is also true. You can have products going to reactants, and this is occurring simultaneously or at the same time. Here's an example. So normally we would read a reaction forward. So we have our reactants turning into our products. We can also read the reverse reaction, which would be sulfur trioxide turning into sulfur dioxide and oxygen. When a reaction is reversible, we're not going to see it written both ways or just be told it's reversible. It's going to be indicated with a special arrow. So again, it's going to have this arrow that indicates a forward and backwards reaction is occurring. This tells me that I can read the reaction going from our reactants to our products as well as our products to our reactants. So keep your eye out for this double arrow. Alright, so equilibrium, you have to have reversible reactions in order to have a equilibrium. But a chemical reaction is at equilibrium or in a state of equilibrium first when you have a forward and reverse reaction occurring simultaneously. And we're going to talk about the two conditions that also have to occur in a second. but there is 3 types of chemical equilibrium that we're going to talk about today. The first and most important being chemical equilibrium, the second being phase equilibrium, and the third being solution equilibrium. Alright, so chemical equilibrium, this is probably the most important slide of the PowerPoint and one of the most important of the chapter. But chemical equilibrium has 2 conditions. The first being the rate of the forward reaction has to be equal to the rate of the reverse reaction. So commit to memory equal rates. This means that our reactants are forming our products and our products are forming our reactants at the same speed. The second condition is the amount or concentration of our products and reactants remains constant. So we have equal rates and constant concentration. Those are the 2 things that you need to commit to memory for equilibrium. When I say constant concentration, this does not mean they are equal. Constant does not mean equal. This means I could have my reactants creating 10 molecules of my products and my products creating only 2 molecules of my reactants. 10 molecules does not equal 2 molecules. It just matters that the 10 and the 2, our concentration remains the same. It is a constant concentration, and it's happening at an equal speed forward and backwards. Here is an example of a chemical equilibrium. This is a pretty classic example. The reason being is that in a test tube, it's very obvious that an equilibrium is occurring. Again, to have a chemical equilibrium, you have to have a forward rate equaling the reverse rate. The concentration of nitrogen tetraoxide and nitrogen dioxide are constant. This is actually what you're going to end up seeing in the lab for this week, but some background info here. Nitrogen dioxide is a brownish red gas. Dinitrogen tetraoxide is clear. When you have an equilibrium, there are conditions that can be set forth where you can favor the forward reaction, so making this product, or you could favor the reverse reaction, making this product. It's very evident with this chemical reaction which one is being favored, because when you favor the forward reaction, you're making a brown gas. Your test tube is literally going to be filled with a brownish red color. When you're favoring the reverse reaction, you end up with a clear gas in your test tube. So again, keep this in mind when you go to do the lab. Our next type of equilibrium is phase equilibrium. When I say phase, I mean state of matter, so solid, liquid, gas. You can have a phase equilibrium between any of your phases. So the example is showing vaporization to condensation for carbon dioxide. You can have a phase equilibrium again between any of the phases. So, for example, freezing and melting. You just have to reach the perfect temperature and pressure for that substance in order for a phase equilibrium to happen. The last type of equilibrium is solution equilibrium. This is only established in saturated solutions, so just a reminder, a saturated solution is when you have as much solute dissolved into your solvent as possible. What this is going to look like is if you make salt water and there's a little bit of solid salt water or salt at the bottom, you have a saturated solution. As much salt has dissolved as possible at that temperature. The rate of dissolving is going to equal the rate of formation of your solid. So for example, here's with a covalent compound. If you're drinking iced coffee, you dissolve solid sugar. Some of it's going to dissolve into aqueous dissolved sugar. And at the same time, some of that dissolved sugar is going to reform into your solid sugar. So your rate of dissolving is equaling your rate of formation. This also happens with ionic compounds, but just a reminder that ionic compounds are going to be dissolving into ions. And your ions can reform into your solid ionic compound. This is what would be happening in our saltwater example. And lastly, one more example. If you have a bottle of soda or tonic water, seltzer, soda or carbonated water has an equilibrium. In fact, you can see it. There's aqueous dissolved carbon dioxide turning into carbon dioxide gas. That's the little bubbles that you're seeing inside the bottle. At the same time, when that bottle is closed, those carbon dioxide gas bubbles are going to be redissolving into dissolved carbon dioxide. So in closed soda bottles, you also have a solution equilibrium. So that's our 3 types of equilibrium: chemical, phase, and solution equilibrium. If you have any questions, please let me know. Otherwise, have a great day.